Good morning, everyone. Greetings from the Root Tutorial Studios, live from a hotel room somewhere near Fermilab. Today we're going to talk about histograms, what they are, why you need them, and how you can get the most out of them. So let's fire things up. So histograms are, in a lot of ways, the most common data type that we're going to use in Root. In some ways it makes sense to start with this, but having done this a few times before, I get better results if we get familiar with Root a little bit before we kind of dig into some of the nuts and bolts about histograms. So let's make a new macro. I'll just call it hist1, and let's play around. So I'll show you what they are, and then we'll talk about some of the details. So histogram, if you haven't been familiar with these before, think bar graph. So we're going to specify some bins or buckets that sort of gives us a range, and we're going to throw things into them, and it's going to give us a really simple way of looking at the distribution of what we've made. So I'll call my histogram variables with something that's got an H, so I'll say new. Now we've got T because all root classes start with a capital T. H is for histogram, 1 is for one-dimensional, and then I get a choice about what we're counting with. So what am I storing my buckets as? So I could do integers or doubles or floats or a few other options. So we'll just do doubles for sort of a normal default. Now let's go remind ourselves what the constructor is. So two ways to do that, like before. If I come to root, I can type th1d double colon, and I can now look at the classes that are inside of th1d, and if I hit tab, it will now tell me what my options are. So name, title, the number of bins, X low, X up, so the range and the x-axis. Of course, the other thing that's worth doing is just opening up a window and Googling root th1, and let's take a look at the documentation real quick. So when I come to th1 is sort of the generic one-dimensional histogram that includes the th1 F and D and I, and it has a lot of documentation that we'll come back to in a little bit. But again, let's see what these things are, and then it'll make a lot more sense. Okay, so the root's internal name, which is going to be the same as my variable name, and now we give it a title, so our first histogram. The next thing is the number of bins. Let's start with something easy, like 5 bins going on an X range from 0 to 5. Now if you do it this way, so the number of bins going from 0 to that same number, you're going to get nice bins that are lined up on the integers. So let's just draw this. Close, and let's execute our macro. So coming back here, .x, I'll type H and I'll tab complete. If it doesn't tab complete, then you've saved your macro in the wrong place, or you've launched root from the wrong place. So that's our quick check. So it's going to set up the X range on the axis that you wanted, and the vertical is going to record the number of counts, the number of times that we've seen something here. So now let's add some data to the histogram. The most common way to do this is with the fill command. So we'll do hfill, and now I just give it a number somewhere on the x-axis. So I could fill in a 3, and let's copy and paste this line a few times. Maybe a 2 and a 2.000004. Okay. So now if I run my macro, I go back and I look at my plot. So I've got my histogram now. In the bin that covers the range between 2 and 3, I have 2 counts in this. In the bin that covers the range from 3 to 4, I have 1 count in this. So when I fill, it takes the number in X, it figures out which bucket or bin that belongs in, and it just increments the count of this. Now this is one of the beauties of histograms. So if I'm going to store 1,000,000 things, and I just record this as an array that has a length 1,000,000, it will take you 1,000,000 bytes or 1,000,000 times 4 bytes to record that data. But now if I shove that thing into 5 bins, I can record all that information in 5 bytes instead of 1,000,000 bytes to see the distribution. So this is an example of what we call data reduction. Okay, so let's do a little bit more. So let's get rid of this. So now let's take a look at what the bin size does, and let's do a little demo so we can see what's going on here. Okay, so let's get a little more room to work with. I'll change this to be 10 bins from 0 to 10. And let's now fill this up with some randomly generated Gaussians. So we'll make a little for loop. So for int I equals 0, I is less than, and we'll just throw in a few thousand, I++. And I'll open up a brace for later, and we'll say h fill, so now I need a number. So we'll use, like we did before, the grandom Gauss to generate some Gaussian distributed random numbers. Let's do maybe a mean of 5 and a width of 2. Okay, and now I'll close that, and Emacs reminds me that I've closed both parentheses. Close, close, and we'll draw. So now I'm going to stuff in 1,000 random numbers into this histogram. Let's run and take a look at the results. Okay, so now I've got my histogram. Let's do a couple of things to play with some of the settings, and then we'll discuss what it looks like. So by default, the y-axis is going to be the range from the lowest level in the histogram to the top level histogram. If we want to change that, then we'll use the set minimum and set maximum commands. You'll sometimes get in trouble if your y-axis doesn't actually start at 0. You'll be accused of trying to bias the plot. So let's now fix that. H set minimum, and we'll make that 0. Okay, what else? Sometimes it can be hard to see that we've got a filled in region here, so maybe you'll want to add a fill color to that. So like we talked about before, I can come to the view colors and I can get the root color wheel, and we can pick something that's visually pleasing for us. So maybe we'll do H set fill color K blue -7. Sure, why not? If you want to see what these options are, again, we can go back to our TH1 page and we can scroll down. There's lots of good documentation at the top that we just blew through, but we could scroll down here to this list of functions inside, and we can look at everything that starts with the word set, which is how we're going to control things. Now if we want to read off a number, we'll use something that starts with the word get. If we scroll through here, though, we also see other things we could do, like get an integral or do an interpolation. Lots of useful things are already built in for us. Okay, so now let's run this one and see where we are. So we've got a lovely looking histogram going from 0 to 200. I've got my bins from 0 to 10. Now let's go ahead and specify what my x and y axes are so we get full credit for our plot. So like before, when I'm giving a title, if I just do a semicolon, I can do my x and y axis titles here. So I'll call my y the number of counts. Alright, now that's looking like a legitimate histogram. If you want to play around with some more options, the other way to do it is to click View and go to the editor and then click somewhere on your histogram. Now to do this, don't click on the body, but click on the line for the histogram. And now you get the histogram options, so now we can set what the line looks like, what the fill looks like. You've got options for plotting errors. There's a lot of ways to visualize this. though normally we just sort of leave things as the default. Okay, the last thing over here in the top corner, we get our statistics box. This thing is incredibly useful in a lot of ways. So, like we said before, histograms are about looking at distributions of variables. So the first thing I get here is the number of entries. So I've called fill on this histogram 1,000 times. It calculates the mean, exactly what you would expect, 5.04. But remember, this mean depends on how many bins I've got. Once I've put a number inside a bin, Root now doesn't remember the numbers that we've actually used. So if I've got a number here between my bins 5 and 6, I don't know if it was 5.1 or 5.9 or 5.5. I just know it was some number that fell into this bin. So when we calculate the mean, it does that by taking the average of the number of counts inside this bin at the center of that bin. So this mean now is kind of the weighted average of all the bin centers. The RMS is the standard deviation, so what's the width of this distribution that we recorded? Now we started with a Gaussian that had a mean of 5 and a standard deviation of 2, so I would expect my numbers here to be about 5 and 2, but our RMS seems a little low. Maybe we can figure out what happened. Now if I right click on this and I go to set opt stat, I get a bunch of 1s, and these 1s tell me what is it I'm looking at. So if I set these to 0, my stat window goes away. But if I add a few more 1s, don't bother counting, just add a few more, I get some more numbers in here that we can take a look at. So let's do that. So now I've added a few other things, underflow and overflow. So if I set up an X range from 0 to 10, if something fell off the edge to the left or to the right, Root's going to count how many did that in my underflow and overflow bins. And now once they're there, they're no longer counted in the statistics or the distributions because Root hasn't recorded what those numbers were or how big they were. So one reason that my RMS is a little low is because we're not counting the tails that have fallen off the end of my graph. Now my entries is 1,000, but my integral is only 992. So if I sum up all the counts in all the bins, I don't have 1,000, I'm missing 8 of them. And the 8 that I'm missing are these 8 that have fallen off the left and the right edge of my plots. Now if you want to go up to higher moments, Root gives you skewness and kurtosis for you, but most people don't really care about that. So if we wanted to not have the statistics window, if this was really just cluttering things up for us, we could just do H, and I could do set stats, and I could say 0, and that thing will go away. If you're doing a lot of histograms, sometimes you don't want that thing at all. If you wanted to control which of the statistics numbers were coming out at you, the way that we do that is not what you would expect. So this set opt stat command that we were using here doesn't live with the histogram, it lives in Root's global style options. So if we wanted to change the default of what we were looking at, I would have to do gstyle set opt stat, and now we could give it all of the 1s. Okay. Alright, so now I get enough to do an overflow and underflow. I seriously never count how many 1s there are. I just type a bunch and see if it was enough. Okay, so now, like I said, let's take this histogram and let's make a few copies of it, and let's take a look at what it looks like to use different settings of bins. So I'm going to take my line here and I'll copy and paste this a few times, and let's call them H1, H2, and H3. So I'm going to start off with one that has giant bins, and then we'll do one that has normal sized bins. I guess normal is a relative term, and let's do this one that has way too many bins. Okay, and I'll just sort of space this out so that we are lined up. So let's make this number be ridiculously small, like 3, and let's do something a bit better here, maybe 100, and let's just go something large. So you can use exponential if you want to do scientific notation here. So let's say 100,000 bins. And let's kick this up from 1,000 to 10,000, so 1e to the 4th. Okay. Now when I am setting this up, I can't have all 3 of these things called h. So let's change this to h1, h2, and h3. All we're going to look at is taking the exact same data but binned in 3 different ways. So what we'll do, just to make sure we're getting the same data here, we'll save our random as some number. So now I'll just take this thing and we'll copy and paste it up here. Okay, and now I'll kill that. So we'll have h1, and we'll just take our number x and we'll stuff it into all 3 histograms. Okay, so I'm setting up 3 histograms which have a different number of bins, 3, 100, or 100,000. I'm going to specify, say, 10,000 random numbers, and I'm going to put this random number into all my histograms, and then we need to come draw them sort of in a side-by-side comparison. So let's just get rid of this for now. Let's make a canvas that has 3 panels, so C1 equals new T canvas. We call it C1, and this will be our bin size comparison, maybe 1200 pixels by 400, so we get about a right 3:1 aspect ratio. C1 divide, okay, C1 CD1, H1 draw, so we'll draw histogram 1 in the first panel, and then I'll just copy and paste these lines a few times. So now we go to the second panel to draw H2, and we go to the third panel to draw H3. Alright, so this might be a good place to press pause and make sure you've got all this typed in, but let's make sure there aren't any bugs before we do this. Okay. Let's embiggen this as much as we can. So again, we're looking at exactly the same data bent in 3 different ways. So I've got the same set of random numbers that I put into 3 histograms. So here on the left, we have all of our numbers stuffed into 3 histograms, and the binning is way too coarse. Pretty much everything here fell in this middle bin, some things fell on the edges. This is pretty worthless. This one on the right obviously has way too many bins. All we see here are a bunch of bin edges side by side by side. If you do way too many, then you'll see holes in between everything. No bin got more than a few counts in it, so the statistical error on each bin is going to be giant. So these are going to be 1 count plus or minus 1. Here in the middle, we get a number that's just right, Goldilocks' third choice, where we have just the right number of bins to really see the distribution. Now, the way that it's normally done is you play around so you get numbers you like. But if you need a rule of thumb to get started, set your X range by knowing what the range is and check the underflow and overflow to see if you missed that. And then the number of bins should be about the square root of the number of counts inside. So going back to our Emacs window, if I do 10 to the 4th things in my histogram, the square root of that is 10 squared, or 100, and the rule of thumb is the square root of the number of entries is about the right number of bins if things are nice and normally distributed. Okay, so let's now move on to one more demo, and then we'll talk about how you set bin contents manually, and we'll wrap this up. So just a quick probability demo that might be helpful practice for you all. So I'm just going to take this and I'm going to save it, and let's study a problem, a really simple probability problem. So the question is, if you roll two dice, two normal six-sided dice, what's the distribution of numbers that you get for the sum of those two? So let's call this dice.c. If you want to, this would be a really good exercise to pause this video, stop, try to do this yourself, and then come back and follow along my answer and see how these look together. Okay, so let's go through this step by step. I'm going to make two histograms now, just so we can see what's going on. I'm going to make one histogram that has the rolls of the individual dice in them, so one die. And we need to have 6 bins that cover my options of 1 through 6. So let's take a look at how we can do this. So we need to be a little bit careful on how we set this up. Let me come back down here to our root. If you have all this garbage here, don't ever be shy of just quitting and restarting to clean things up. Okay, so let's suppose I were going to make a new histogram. If all I have are integers, then I can make this a th1i instead of a th1d, but that really won't matter. So we'll do h, and we'll just make a little test. So let's suppose now I want to store the numbers 1, 2, 3, 4, 5, 6 in my histogram. Well, maybe I do 6 bins from 0 to 6. Let's take a look at what that looks like. Now, if I roll a 6, is that going to come here, or is it going to come here? Well, maybe we've fallen off the edge, and I don't need this one that goes from 0 to 1. That's kind of confusing. So maybe I wanted to go from 1 to 7. So now, what would that look like? If I go from 1 to 7, now if I roll a 1, am I sure it's going to be put to the right here and not off the left edge? I have plenty of ranges for 6, but not for my number 1. So one really, really nice trick here that I would like you all to do. Whenever you're plotting integers, let's offset everything by half of a bin so that the bin centers sit on top of the integers. So we're going to do 6 bins, and we're going to go from 0.5 to 6.5. So that way, the first bin is centered at 1, and the last bin is centered at 6. Okay, now let's roll some dice. So I'll start off with just a few numbers. So I need some easy way to have root roll some dice for me. The G random is the global random generator. And if you ever want to look at what the options are, all we have to do is type in root T random, because T random is the class, and go to the reference, and we can see what all the options are here. What I'm going to want for dice is just integer. And so now let's see what integer looks like. So I'll search on the page for integer. Returns an integer from 0 to maximum -1. So if I do grandom integer 6, that's going to give me a number between 0 and 5. So I'm going to do integer 6, I'm going to have to add 1 to that to get something that simulates what a dice roll would be like. Okay, so let's just call this integer roll 1 is grandom integer, and this was going to be 6 plus 1. So this gives me a number between 0 and 5. I add 1 to it to get a number from 1 to 6. and we'll fill this roll into our histogram. Okay. Now next I'm going to go from rolling 1 dice to rolling 2 dice, and I'll save the sum of those dice into a second histogram. So let's just go ahead and finish editing this. Whenever possible, program by copy and paste. Life is way too hard to start from scratch every time. So I only need 2 panels instead of 3, and I don't have my second histogram yet. Okay, so now let's do a test here and let's see if our rolling 1 dice is working well. So we called this macro dice.c. Okay, so if I roll 1 die here, and I rolled it 10 times, I got 2 2s, 2 3s, 3 4s, 3 5s. I didn't get any 1s or 6s. Was that a statistical fluke or a bug? Hard to say. We can roll this a few more times. Oh, now I got a 1 and I got some 6s. If we want to see it better, I could just increase my number of rolls and we should get a nice uniform distribution. I still think that histograms are a little easier to see if we give them a fill color. So now let's try this. Okay, and now this looks choppy and all over the place, but remember the y-axis is going from the minimum to the maximum, so it doesn't start at 0. So I can see the relative heights, but I can't tell if this really is a uniform looking distribution or not. So now let's come back and do h1 set minimum 0. Okay, and while we're here, let's set the x and y axis values. Okay. And I'd probably want to turn the statistics box off. So now I've got 1 die, I'm rolling it 10,000 times, and I got a pretty uniform distribution between 1 to 6. If I go to set opstat and I add a few more 1s here, I have no underflow, no overflows, I haven't missed anything. Alright, so now I've got a setup where I can roll 1 die, and it seems fair, it seems reasonable. You always want to test your code with reasonable things before you move along. Okay, let's make this now to do 2. I will take a second histogram. We will do 2 dice. Now this has to go not from 1 to 6, but we need to go all the way up to 12. Instead of rolling 1, we're going to roll 2. We'll go ahead and save both rolls inside our first histogram, so I have a record of everything that was done. And then we will add the sum, R1 plus R2, into the second histogram. And we'll draw it. Let's also set these style options here. If my 1 die is blue, maybe I'll have the 2 die be red. Okay. So now let's take a look and see what we got. So I rolled now 2 dice 10,000 times. So I have 20,000 total rolls. And the sum of both dice gave me a distribution that looks like this. Does it work out to be what we expect? Well, the least common options are 2 and 12. I only have one way to do those. I either have to get 2 1s or 2 6s. My next most commons are 3s and 11s, because now I have 2 options to make a 3. I do a 1 2 or a 2 1, and I have 2 options to make an 11, either a 6 5 or a 5 6. The most common one, if I go to View and Event Status Bar, it'll show me the X and Y axes here. So this is the bin number 7. because I have the most options with 2 dice to make a 7. 1, 6, 2, 5, 3, 4, 4, 3, so on and so forth. And so the mean is set right here at 6.975, which is right at about 7. So I could prove that the most likely number is 7, and I can see how much more likely that is than any other option. Okay, so that was just a quick little demo on what you could do with histograms and probability. One quick thing, and then we will wrap this up and call it a day for an overly long tutorial. So, last thing, suppose I actually want to take these numbers and write them down or save them or record them. I don't want to try to do this manually, but maybe let's output these to the screen. Root has functions for reading these off called getBinContent, and I could use a similar function manually called setBinContent to put whatever I wanted inside a bin. So let's do that. So down here at the end of my code, let's maybe have it output the bin counts to the screen. Okay, so we'll do cout counts for sum of 2 dice, end line. So now we need to do a for loop over all of the bins. So we'll do for, and I'll do I equals. And now we need to be careful about how we handle this next loop here. So I equals, going back to my plot, this leftmost bin in root's internal system is bin number 1. The rightmost bin is the nth bin. So if I have 10 bins here, then the rightmost bin would be bin number 10. But remember, there's also an underflow and overflow. So in root system, the 0th bin is the underflow on the left, and the n+1 bin is the overflow on the right. So if I have 10 bins, I want my loop to go from 1 through 10. So we'll start at 1 here. Now, a good practice to do is to not hard code the number of bins, but to have root tell me how many bins there are in a histogram. So if I change it, I don't have to change it again down here. So let's use the getNumberOfBins function to see what that looks like. So we'll do h2 get, and now let's take a look. th1 get in, and I hit tab. So we talked about how root almost always starts things with capital letters. This is one of the really annoying exceptions. Get in bins, where bin has a lowercase b instead of an uppercase b. That is kind of annoying to me. Now, we only have a one-dimensional histogram, so we're going to use get in bins x for the number of bins on my x-axis. Get in lowercase b, x, capital X, and don't forget to do open and close parentheses. Okay, so as long as I is less than or equal to that, I++. So now I've got this loop over the number of bins, so let's output what we have. Okay, so we will cout. Let's start off by outputting what I is, and then maybe we'll tab over. And now let's do h2 get bin content, what's in the ith bin, end line. We'll close this. We'll add one more thing to that in a little bit, but now let's take a look at what we got. Okay. So in my bin number 1, I have nothing. In my bin number 2, I have 253 counts. In my bin number 3, I've got 5. That seems like it's working really, really well. Now, we have happened to end up in a world where my bin number 1 actually is centered on number 1. If your histogram wasn't set up this way, we could have root tell us what the center of these bins is by using the get bin center. So if I do get bin tab, I could do get bin center, content, error. I could get the width, the low edge, the high edge. There's a lot of things we can do with this. So if I wanted to know what the actual center of the bin was, maybe I do h2 get bin center I, and now another tab, and we'll throw in the final bin content. And I guess just for fun, let's manually change one of the bins. So let's go in and change nature's random number generator, h2 set bin content. What shall we do? Let's make this bin be ridiculously large. So maybe I suppose 4 actually has 2,000 counts in it. Okay. So now my bin number 1 is actually centered at a value of x equals 1, and it had only 1 count in it. We went in and manually changed bin 4 to have 2,000 just because we can. And now I've got the number of entries here is 10,001 because of what we've done to this now by using the set bin content function. Okay. So I think that more than covers a quick overview of histograms. The only thing we haven't talked about here is doing two-dimensional histograms. So that pattern follows just like going from a TF1 to a TF2. That would be a root TH2 to make a two-dimensional histogram. But we'll take a look at some more of these details next time. All right, thank you all for listening.